product of the limits. So this is the same as the limit of e to the x as h tends to 0 times the limit of e to the h minus 1 all over h as h tends to 0. And we can actually evaluate this particular limit here. The function e to the x has no h in it. So irrespective of what's happening to h, the evaluation of e to the x is going to evaluate to e to the x as h tends to 0. The tending of h to 0 will have no effect on this evaluation because there's actually no h in here, if that makes sense. So therefore what we have is f prime of x is equal to the evaluation of this part, let's say, of this part of the product, okay, as h tends to 0, well, e to the x tends to e to the x. So this is e to the x times, and this particular limit here, the limit of e to the h minus 1 all over h as h tends to 0. So to get the first derivative, or to get the derivative of this particular function, f of x is equal to e to the x, it's actually now boiling down to finding this particular limit here. Okay. So what we can actually do is we can actually look now at the Taylor expansion of e to the x, in this case where x is h. So therefore we have, therefore what we have is, therefore we have f prime of x is equal to e to the x times the limit, and the Taylor expansion of h is 1 plus the Taylor expansion of e to the h is 1 plus x over factorial 1, which is effectively h over factorial 1, plus h squared over 2 factorial dot 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 minus at the end here, we're going to be minusing the 1 all over h. Okay, I'm just going to get rid of my phone there, so apologies there, guys. All over h. I'm just actually going to mute that so that doesn't happen again. So all over h as h tends to 0. And what we're going to do is we're going to, this particular denominator here, we're going to break it up across this. So this becomes, therefore, don't forget the 1 minus 1 cancels. So what we're left with here is we're left with f prime of x is equal to e to the x times the limit of, well, it's going to be h over 1 factorial divided by h is the same as 1 over 1 factorial, which is the same as 1. Okay? Plus h squared divided by 2 factorial is the same as, and divided by h, okay, is the same as h over 2 factorial, plus the next term would be h squared over 3 factorial. The next term would be h to the cube over 4 factorial, and that goes on to infinity as h tends to 0. And don't forget the limit of a plus b is the same as the limit of a plus the limit of b. So we can evaluate each one of these particular terms, okay, individually. But effectively, you can actually see what happens here is that as h tends to 0, each one of these terms have a h in it. So we have 0 divided by 2 factorial is 0. 0 squared divided by 3 factorial is 0. And ditto, that particular pattern is going to continue out to infinity. And what we have is a summation of zeros, which is going to be 0. So it actually this ends up as therefore we have f prime of x is equal to e to the x times, and the limit of 1 as h tends to 0, the limit of a constant as h tends to 0 is just a constant, so we have times 1, and therefore what we have is f prime of x is equal to e to the x. Okay? And that completes the particular proof that we have. This particular proof is is relying upon this particular Taylor expansion of e to the x. There is another proof that we could have. So effectively, really what we're saying from this particular proof is that this particular limit here tends to 1. Okay, so effectively what this is saying, is this, is that, whoops, daisy, okay, is that this particular limit, let me just cross this over here, this page, okay. So effectively what we have here is that the limit of e to the h minus 1 all over h as h tends to 0 is effectively equal to 1. That's what the Taylor expansion of e to the h is actually telling us. I mean, there's